So in the last session we proved a sufficient and necessary and sufficient condition for a field to be a splitting field over another field. So we'll do some corollaries of that theorem. So the first one is let E be a splitting field over F. This is F closure. Then every irreducible polynomial in f of x that has a 0 in E splits E. So all it says is that every irreducible polynomial that has a 0 in f of x, so 0 in E will split the field E, meaning that all the zeros, if one 0 is in E, all the zeros are in E, if E is a splitting field. So let P of x is equal to the irreducible polynomial of alpha over f, where alpha belongs to E. And let beta be a 0 of P of x, meaning beta could be alpha or any other 0 of P of x. This implies there exists a conjugate isomorphism from f alpha, we'll write it as sigma psi of alpha beta from f alpha to f beta, such that psi of alpha beta of alpha is equal to beta. What I'm trying to say is this is our F closure, this is our F, this is our E, and there is an alpha here. Then there is a simple extension containing alpha. Then there is a conjugate isomorphism alpha beta, and that is, this is F closure. We are not sure F beta is inside E, so we'll write it as beta here. So this is psi of, this is actually f of beta. So this actually means, so this is an isomorphism, and F closure is algebraic over f of alpha. So we can extend to f closure. This means psi alpha beta can be extended to an isomorphism from isomorphism tau from f closure to a subfield of f closure. We'll write it as f closure to tau of f closure. This is an isomorphism, so we can always have a inverse isomorphism. So inverse isomorphism from tau of f closure to f closure is an onto isomorphism. So we can again, so that means there is an isomorphism here tau from f closure to a tau of f closure. Then there is another isomorphism tau inverse from tau of f closure to the whole of f closure, and that can be extended to f closure. But since this is an onto function, tau of f closure is equal to f closure. We already established these facts earlier. So this implies tau of f closure is equal to f closure implies tau is a automorphism. And because since E is a splitting field, using the previous theorem, tau induces an automorphism in E. Right? That implies what is the definition of tau within E? The tau restricted to E is nothing but psi of alpha beta, because tau is an extension of alpha beta. So that implies psi of alpha beta of alpha is equal to beta that belongs to E. That means B is a zero of every zero is zero of P of x belongs to E, implies E is a if every zero of P of x belongs to E implies P of x can be factorized into linear polynomials in E of x, implies P of x splits we'll do couple of examples using this corollary. Let f is equal to q and E is equal to q of root 2. So we know that q of root 2 is a splitting field. Over q, because x square minus 2 has all zeros in q of root 2. Definition of splitting field is if there is a collection of polynomials such that all the zeros of all the elements of the polynomials are in that set, then it's that field, then it's a splitting field. So x square minus 2, since all zeros of x square minus 2 is in q of root 2, and q of root 2 is the smallest such field. Now we'll take and again x square minus 2 is an irreducible polynomial. In q of x, because it cannot be factorized into a polynomials in q of x. And root 2 is a 0 of p of x, or x square minus 2. That implies x square minus 2 splits q of root. In other words, if root 2 belongs to q root 2, then its conjugate minus root 2 also belongs to q. All the conjugates of root 2 should belong to q root 2. That is the time we say that x square minus 2 splits q root 2. We'll take another example. F is equal to q, but E is equal to q of root 2 comma, no, not root 2 comma, we'll take q of cube root of 2. Here E is not a splitting field. Why? Because you cannot find a polynomial here such that all zeros belongs to irreducible polynomial here for which all the zeros belongs to E. If you take x cube minus 2 is an irreducible polynomial in q of x, and the real zero of x cube minus 2 is in Q of cube root of 2. This x cube minus 2, we can write it as x minus cube root of 2, the real one, which normally we'll say is alpha 1, x minus alpha 2, x minus alpha 3. Alpha 2 and alpha 3, where alpha 1 is equal to cube root of 2, and alpha 2 and alpha 3 are complex zeros of x cube minus 2. See here, because q of cube root of 2 is not a splitting field over Q. This is not a splitting field over Q. So even if cube root of 2 belongs to Q of cube root of 2, does not imply alpha 2 and alpha 3 belongs to cube root of 2. Meaning alpha 2 and alpha 3 are not in here, even if one root is in cube root of q of cube root of 2. That is because q of cube root of 2 is not a splitting field. Here q of root 2 is a splitting field. Here q of cube root of 2 is not a splitting field. See, what is alpha 2 and alpha 3? Alpha 2 is equal to cube root of 2, the real cube root of 2, times minus 1 plus I root 3 by 2. And alpha 3 is equal to cube root of 2 times minus 1 minus I root 3 by 2. These are complex zeros of this. What is needed to make E a splitting field? What is missing here? See, in q of cube root of 2, this is already there, and half is already there. So the thing which is missing here is I root 3. So if you adjoin I root 3 to this simple extension, E will become a splitting field. To make E a splitting field, adjoin E with I root 3. That means if E is equal to q of cube root of 2 comma I root 3, then E is a splitting field over Q. And that implies alpha 1, alpha 2 and alpha 3, both all the zeros of this irreducible polynomial belongs to E, that is equal to q of cube root of 2 comma I root 3. And that means x cube minus 2 splits. Here the cube root of 2 does not split E because E is just this one. But if you adjoin I root 3 to this, then E will become a splitting field. So x square minus 2 will split E. We'll do one more corollary of our theorem. If E is a splitting field over F, then every isomorphism from E to a subfield of F closure is an automorphism. And if E is a finite extension, then the index of E over F is equal to the order of the group of automorphisms on E over F. So this is very simple actually. So what we will do is this is our F closure, F and E. E is a splitting field of F. Then this is our F closure, this is our F. Then any isomorphism from E, this is our sigma of E. Any isomorphism E to a subfield of F closure will become an automorphism on E if E is a splitting field, meaning this is equal to E. So we'll do the proof. Let sigma to sigma of E be an isomorphism from E to a subfield of F closure. Naturally, you can extend this one to a toe. So sigma can be extended to toe from F closure to a subfield of F closure, and that is F closure to toe of F closure. Toe inverse is an isomorphism from toe of F closure to F closure, and toe inverse is onto. Same argument. So toe inverse is this. So this is our toe. So toe of F. So toe inverse can be extended to F closure to an isomorphism from F closure to a subfield of F closure, since tau inverse is an onto isomorphism, tau of F closure is equal to F closure. Same argument as we did earlier. But E is a splitting field. E is a splitting field implies tau induces an automorphism in E. But tau is an extension of sigma, implies sigma is an automorphism. And that is a proof. Now the next one goes directly from this result. The index of E over F by definition is the number of isomorphism from E to a subfield of F closure. It is independent of the isomorphism itself. It depends only on E and F. And each isomorphism is an automorphism. So when E is a finite extension of F, E of F is equal to the number of automorphisms on E using this result, and that is nothing but G of E over F, the order of E over F. Now we will do a problem. Find the splitting field and its degree over Q of x to the power of 4 minus 1. Splitting field of a polynomial means if f of x belongs to f of x, then the splitting field of f of x is E if E is the smallest field containing all zeros of f of x. So x to the power of 4 minus 1 is equal to x minus 1 times x plus 1 times x minus I times x plus I. So the zeros of x to the power of minus 1 are 1, minus 1, I, minus I. So Q contains 1 and minus 1. So to find the smallest, so the splitting field, to find the splitting field, find the splitting field of x to the power of 4 minus 1 adjoin I to q. That is q of I, meaning the simple extension of I over q. What is simple extension of I over q? It is the smallest field containing I. So the splitting field is q of I. So the splitting field of x to the power of 4 minus 1 over q is q of I. Let us do another problem. Find the order of the following groups. The first one is group of q of cube root of 2 over q. Second one is group of q of cube root of 2 comma I root 3 over q. 3 is group of q of cube root of 2 comma I root 3 over q of cube root of 2. This is actually the group of automorphisms on q of cube root of 2 leaving q fixed. So here this is q closure, this is q, and here cube root of 2, and here you have cube root of 2. So this is not a splitting field of q of cube root of 2 is not a splitting field of q, meaning there are some isomorphism from here that may not be an automorphism. So every automorphism, on q of cube root of 2 depends on cube root of 2, because q of cube root of 2 is generated by 1 and cube root of 2. The elements of this one is actually a plus b cube root of 2 plus c cube root of 2 whole square. A, b, c in q. So it's generated by 1 and cube root of 2. And 1 is already mentioned here. because q is fixed. When you give 1, that generator generates this q. So the only element that comes outside q, or elements come outside q, are generated by cube root of 2. So automorphism, so another thing is, every automorphism should map cube root of 2 to its conjugate that is in cube root of 2. There are 3 conjugates for this. 1 real conjugate and 2 complex conjugates. Complex conjugate does not be an element of this. It's not an element of this. Because we are considering only automorphism, we cannot map cube root of 2 to a complex conjugate. So the only that is in E, that means it should map to its real conjugate, and that is cube root of 2 itself. So there is only one automorphism on cube root of 2 that maps cube root of 2 to an element in cube root of q of cube root of 2. So, and that is the identity automorphism on q of cube root of 2. So this is actually, the order is equal to, so the order of g of q of cube root of 2 over q is equal to 1. This is actually the group of automorphisms on q of cube root of 2 I root 3 leaving q fixed. So this is actually enlarging this field to include I root 3. So here, what you do is q of cube root of 2 comma I root 3 is generated by 1 cube root of 2 I root 3. And the conjugates of cube root of 2 are cube root of 2 comma I root 3 cube root of 2 comma, this is the real conjugate. Then other conjugates are cube root of 2 times minus 1 plus I root 3 by 2 and cube root of 2 times minus 1 minus I root 3 by 2. We'll take this one as alpha 2, this is alpha 1, and this is alpha 3. So here, not like this, you can now map any conjugate to any conjugate. So what I'm saying is alpha 1 can be mapped to alpha 2, alpha 1, alpha 2 and alpha 3 because all these three are in here. So there are more possibilities to create an automorphism. So the automorphisms are sigma 1 that maps sigma 1 alpha 1 to alpha 1, sigma 1 alpha 2 to alpha 2, sigma 1 alpha 3 to alpha 3. That is one. Second one is, this is same, but here you change to sigma 3 and sigma 2. Now we change here 2, and this will be sigma 1 and this will be sigma 3. Keep this one as same. This will be sigma 3, sigma 1. And the next one will be sigma 3, alpha 3, this is actually alpha sigma 1, sigma 2, this is sigma 3, this is sigma 4. So sigma 5 of alpha 1 is equal to alpha 3, sigma 5 of alpha 2 is equal to alpha 1, sigma 5 of alpha 3 is equal to alpha 2, and sigma 6 alpha 1 is equal to alpha 3, sigma 6 alpha 2 is equal to alpha 2, sigma 6 alpha 3 is equal to alpha 2. So there are 6 automorphisms. So the order of G of cube root of 2 comma I root 3 over Q is equal to 6. See, this is a splitting field of Q. This is not a splitting field of Q. So any isomorphisms from here going here will be an automorphism. And there are 6 such isomorphisms. Here there are more isomorphisms, but only one of them we can use it as an automorphism. The others will go beyond Q of Q root of 2. The last one, we can regard this one as G of Q of I root 3 over Q, because we have a cube root of 2 here and a cube root of 2, so you are fixing cube root of 2 instead of Q. So this is same as this. So one way to find out is to find out the irreducible polynomial. The irreducible polynomial of I root 3 over Q reducible polynomial of I over Q over Q, and that is irreducible polynomial of I root 3 comma Q is equal to, how do you find it? We'll take x equal to I root 3. So x square is equal to minus 3, x square plus 3 equal to 0. So it is actually x square plus 3. the zeros of x square plus 3 are I root 3 and minus I root 3, and both belongs to Q of I root 3. So the automorphisms on Q of I root 3 is determined by one comma I root 3. So one automorphism will be I root 3 to I root 3, and the second one is I root 3 to minus I root 3. It has to map to its conjugate. So the order of g of cube root of 2 comma I root 3 over q of cube root of 2 is equal to this is actually q of is equal to